Okay, so now that we've seen the experimental setup for how we control which product we get from the primary alcohol oxidation, we can start to write equations for these reactions. So we'll start off with reaction A, where we're taking the primary alcohol to the aldehyde. So the way we write these equations sort of takes a little bit of getting used to and looks a bit unusual to start with. What we do is we write the formula for the alcohol. I've shown it as a displayed almost. I haven't shown the bond between the oxygen and the hydrogen there, but it's other than that, it's a displayed formula. Obviously, you could show it as a skeletal or a structural, but we've got the alcohol, primary alcohol, and then you can see that we've got O in square brackets, which is, as I say, a bit unusual. And the reason we do this is because the substance that we add to cause this reaction to occur is providing an oxygen atom. Now, the formula for the substance, as you'll see in a moment, is a little bit complicated, and it's not really relevant to what's going on with the organic chemistry. All that's important is that this substance, this oxidizing agent, all that matters really is that it's providing an oxygen atom. So conventionally in these equations, we just write that oxygen atom and we put it in a square bracket just to show that it's coming from another substance. It's not just an oxygen atom floating around on its own, but it's all that's important for this organic chemistry reaction, so it's all we're going to show. And then you can see that we've got the aldehyde as our product, okay, we named it up there, ethanal, and water is the byproduct. And you can see there that everything is balanced because we've got the right number of carbons on each side, 2 and 2. We've got the same number of hydrogens on each side, and if we count up our oxygens, there's one there, one there, one there, one there. Okay, so actually thinking about this in terms of what we said a moment ago, whether or not it's an oxidation reaction, we can see that it is, because what's happened to our organic substance is that hydrogen has been removed. We've gone from this to this, so it's lost hydrogen, which is an oxidation. Now, the O in square brackets, as I say, represents an oxidizing agent. Now, you do need to know what that oxidizing agent is. Now, it's a mixture of a substance called sodium dichromate. We could use potassium dichromate instead, and you need acid in there as well, which is typically sulfuric acid. Now, the formulae of this substance, though, this sodium dichromate, is this one, Na2Cr2O7. You do need to know that formula. If it's the potassium version instead of the sodium version, it's a similar formula. Okay, it's just K2 instead of N2. Now, either of those, doesn't matter which one you use, this actually splits up and provides what we call the dichromate ion, okay, which is Cr2O7 2-, and it's that ion mixed with the H+ ions from the acid that is what we call this oxidizing mixture. So those substances, those ions, are what produce this O in square brackets. You do not need to know how that works or how that happens. It's complicated, so we're not even worrying about it at this stage. You just need to know that these are the substances that you need. You need to know the formulas of them, and you need to know the names as well, okay? But in terms of writing the equation, we just write the O in square brackets. Now, we also need to know, so there we go, we can just call that, acidified dichromate if you want to name it in another way. Okay, you can either name the individual chemicals or you can talk about acidified dichromate. Now, the other thing I was just going to mention there was that if we want to produce the aldehyde, as you've seen when we were looking at the diagrams of the experiments, we need the distillation set up. Okay, so you remove that aldehyde as soon as it forms and prevent formation of the carboxylic acid. If we could see, and you'll see on the YouTube clip in a moment, if you could see this stuff, the acidified dichromate, it's bright orange to start with. When it does its job and it causes something to be oxidized, as it has done here, it turns green. Okay, so orange to green is the colour change that you need to know there. Okay. Now, moving on to equation B, okay, when you're taking the primary alcohol to the carboxylic acid. Okay, this time, because we're going 2 steps in the oxidation process, we're adding 2 lots of O in square brackets. We still produce water, okay, and again you can see if you count up all the oxygens, all the hydrogens, all the carbons, the equation is balanced for each of those 3 elements. Now this is where it gets a bit simpler because O in square brackets is exactly the same as it was before. It's the same substance, so it's exactly the same, okay? It's just now, in order to get the carboxylic acid, we need to make sure we've got the experiment set up for reflux conditions, not distillation. Okay, so reflux. The colour change is the same, so that makes life easy for remembering your observations. Now, that's the point where we can move on to look at secondary alcohols. Now, in fact, secondary alcohols are much simpler to deal with. So once you've got your head around what's happening with primary alcohols, this bit should be easy, because secondary alcohols do not have this possibility of 2 products. There is only one possible oxidation product for a secondary alcohol. Now, I'm going to go straight to the equation that you now recognise with the O in square brackets. If we start with a secondary alcohol, so you can see here that we've got propan 2-ol, then what happens with this, when we oxidise this substance, then what we do is we form, like we did in the first stage of the primary alcohol, we form a C double bond O here, and in order to do that we have to lose this hydrogen. So we lose the hydrogen off the alcohol and the other hydrogen off that carbon atom. So this forms this C double bond O, but this time the C double bond O is in the middle of the molecule rather than on the end, which means that this substance is a ketone. In particular, this one is called propanone. Water is formed as well, and you can check that it's balanced by adding everything up as before. Now, for these secondary alcohols, the ketone is only the only possible product. You can't take it to a carboxylic acid. And in terms of memorising other bits of information, well, it's pretty straightforward now, as long as you know the other for the other reactions, because O in square brackets is provided by the exact same substances as it was for the other reaction. It's acidified dichromate again. The conditions are less important here because you haven't got this difficulty of trying to control which oxidation products you get, because there is only one. So you don't need to really worry about whether or not it's distillation or reflux, and you probably wouldn't be asked. If you were asked, either wouldn't really matter because there is only one possible product. The observations are the same, orange to green, because we've got the same oxidising agent, the acidified dichromate, and it's done its job, and it goes green when it does its job. Finally, just for completion here, tertiary alcohols. Well, tertiary alcohols cannot be oxidised in this way. Now, the reason for that is because if we look at the structure of a tertiary alcohol, if we think about what happens in the first stage of this type of oxidation, we form a C double bond O where we have the alcohol. Now, in order to do that, if we think about, crossing that hydrogen off and putting the double bond in here, well, if we did that, then this carbon in the middle would have too many bonds. It would have 5 bonds, not 4, and carbon can only have 4 bonds. So the only way to make that work would be to break one of these bonds. Now, these are all carbon to carbon bonds, which are strong, and it's quite difficult to break carbon to carbon bonds. It's certainly not going to happen with these chemicals and with this type of reaction. So it doesn't work, it doesn't happen. Tertiary alcohols won't undergo this type of oxidation. Okay.